And to appreciate the sleek, monolithic architecture of the Raptor No. 3, one must first confront the visceral, chaotic reality of its ancestor, the Raptor No. 1. In the world of software development, there is a concept known as the prototype phase, the stage where functionality is the only metric that matters, and elegance is a luxury the schedule cannot afford. If the Raptor No. 3 is a polished, compiled, executable running in a hardened production environment, the Raptor No. 1 was the source code in its rawest form, littered with print statements, experimental libraries, and to-do comments made manifest in stainless steel and Inconel. And in 2016, when SpaceX first test-fired a subscale version of the Raptor, and later in 2019, when the first full-scale units began screaming to life on the stands at McGregor, Texas, the aerospace community saw something that looked less like a finished engine and more like a laboratory experiment gone rogue. It was a dense, impenetrable thicket of tubes, wires, sensors, and valves. To the uninitiated, it was a mess. To the engineer, it was a spaghetti prototype, a necessary, high-fidelity proof of concept designed to solve the most difficult equation in chemical propulsion, the full-flow staged combustion cycle. And the architecture of verifiability. The primary objective of the Raptor No. 1 was not mass production, nor was it weight optimization. Its objective was validation. And as we explored in our deep dive into the full-flow staged combustion cycle, the physics of running both oxygen-rich and methane-rich pre-burners is a high-wire act. In a traditional engine, you might have a handful of critical data points to monitor. In the Raptor No. 1, the engineers were flying blind into a regime of pressure and temperature that had never been sustained in a flight-ready engine. Consequently, they instrumented every square inch of the machine. And imagine a custom-built gaming PC where the builder is obsessed with overclocking. Instead of a sleek case with hidden cable management, the components are spread across a test bench. There are external thermal probes taped to the RAM, flow meters spliced into the liquid cooling loops, and a dozen extra fans zip-tied to the chassis just in case the voltage spikes. This was the Raptor 1. It was covered in hundreds of external sensors, pressure transducers, thermocouples, and strain gauges, each with its own dedicated wiring harness. And this spaghetti of instrumentation was the engine's debug mode. SpaceX needed to know exactly how the gas behaved as it transitioned from the pre-burners to the main chamber. They needed to see the latency between a valve command and a thrust change. To get that data, they had to bypass the desire for a clean silhouette. Every external wire was a log file that would eventually allow them to delete the sensor in later versions once the behavior was characterized. In the plumbing of a Pioneer, the most striking visual element of the Raptor 1 was its external plumbing. In a refined engine, fluid paths are often integrated into the housing or routed through internal galleries. In Raptor 1, the propellant lines were bolted on like an afterthought. And there were massive, looping bypass lines and auxiliary pipes that crisscrossed the engine's midsection. These were the global variables of the propulsion system. Because the team hadn't yet perfected the inline logic of the fluid flow, they used external lines to balance the pressures between the oxygen and methane turbopumps. If the oxygen side was running too hot, a bypass valve exposed and vulnerable would shunt flow to compensate. And this made the engine incredibly heavy and fragile from a systems integration standpoint. In the Anatomy of a Rocket, Chapter 1.2, we discussed how every gram of dry mass on an engine is a gram of payload that never reaches orbit. The Raptor 1 was a heavy lifter, but it carried its own weight like a burden. It weighed significantly more than the Merlin 1D engine. It was designed to succeed, not just because it was more powerful, but because it was over-engineered for safety and data acquisition. And the complexity was a byproduct of the full-flow staged combustion cycle's inherent difficulty. Because the Raptor 1 had to manage two separate turbopumps, each essentially a high-powered jet engine, in its own right the synchronization hardware was immense. It required a suite of redundant valves to ensure that if one pre-burner stuttered, the other wouldn't cause the entire engine to hard crash, meaning an explosive disassembly. These redundancies added to the spaghetti aesthetic, creating a profile that was wide, jagged, and difficult to shield during the high-velocity re-entry Starship would eventually face. In performance specs, the raw power of the Beta, despite its unrefactored appearance, the Raptor 1 was a triumph of raw physics. It was the first engine of its kind to reach flight readiness, proving that the theoretical benefits of the full-flow cycle could be translated into real-world thrust. And at its peak, the Raptor 1 was capable of producing approximately 185 tons, or 1.8 meganewtons, of thrust. To put this in perspective, this was already significantly more powerful than the Merlin 1D, which produces about 85 tons. However, it achieved this power at a compute cost that was unsustainable. The chamber pressure hovered around 250 to 260 bar, impressive, but far below the 350 bar target of the Raptor 3. And the engine was also leaky in a metaphorical sense. The complexity of the external seals and the sheer number of bolted joints meant that the MTBF, or mean time between failure, was low. It was an engine that required constant patching. After every test fire at McGregor, technicians would have to swarm the engine, checking the hundreds of spaghetti lines for leaks, cracks, or signs of thermal fatigue. It was a high-maintenance asset, the opposite of what is required for a rapidly reusable Mars-bound fleet. And the technical debt of the first generation. In software, technical debt occurs when you choose a quick, messy solution now over a better, more time-consuming approach. Raptor 1 was a mountain of intentional technical debt. And the SpaceX engineers knew that the external sensors and bolted-on plumbing were not the final solution. But they also knew that if they spent 5 years trying to design the perfectly integrated engine from day one, they would never get off the test stand. They chose to build the spaghetti version first to compile the physics. And one of the most significant pieces of debt was the manifold design. In the Raptor 1, the manifolds, the junctions where propellants are distributed into the injectors, were massive, heavy castings. They were designed with huge safety margins because the team didn't yet have the runtime data to know exactly how much stress those parts would endure. They were over-provisioning the hardware. And furthermore, the Raptor 1 utilized a complex series of purge systems. Because the engine was so intricate, it had many dead zones where propellant could pool and potentially explode during ignition or shutdown. To solve this, they added even more plumbing nitrogen and helium purge lines that would flush the cache of the engine after every run. This added another layer of spaghetti to the exterior, making the engine look like it was caught in a web of its own making. In the Starhopper era, code in the wild. The true test of the Raptor 1 spaghetti prototype came with the flight of Starhopper, the snub-nosed, stainless steel water tower that served as the first flight test vehicle for the Starship program. And in August 2019, a single Raptor 1 engine, serial number 6, lifted Starhopper 150 meters into the air. This was the moment the prototype became a product. Watching that flight, one could see the external components of the engine glowing under the heat of the exhaust. The sheer amount of exposed surface area on the Raptor 1 meant that it was highly susceptible to secondary heating, where the heat from the plume bounces back and cooks the engine's own external wires and tubes. And this flight highlighted the scaling bottleneck. While the Raptor 1 worked for a single-engine hop, imagining 33 of these engines clustered together at the base of a super-heavy booster was a nightmare. The internal interference, or EMI, from 33 sets of spaghetti wiring alone would have been a signal processing disaster. If one tube on one engine leaked, it could trigger a cascade failure across the entire cluster. And the Raptor 1 had proven the logic, or the full-flow staged combustion cycle, but it had failed the deployment test. It was too complex to build, too heavy to fly efficiently, and too fragile to reuse without a total reboot. And the lessons of the mess, the Raptor 1 was never meant to be the final release. It was a minimum viable product, MVP, in the most extreme sense of the term. It taught the SpaceX team several critical lessons that would define the transition to Raptor 2 and eventually Raptor 3. And sensor redundancy versus integrated health monitoring. They learned which 90% of the sensors were unnecessary once the model was understood. Thermal management. They realized that external plumbing is a liability in a high-heat environment. Everything must be internalized. The flange problem, every bolted joint or flange, is a potential leak point. To reach 350 bar, they would need to move from bolted to welded and unitized structures. The mass spiral. They saw how complexity in one area, like the pre-burners, forced complexity in another, like the cooling system, leading to a heavier engine that required more thrust, which in turn required more cooling. And Raptor 1 was the first draft, the essential, messy, brilliant, and overcomplicated foundation upon which the future of the program was built. It was the spaghetti code that allowed the engineers to understand the algorithm of thrust. Once they understood the algorithm, they could begin the process of refactoring, stripping away the external sensors, merging the fluid paths, and turning the chaotic spaghetti into a streamlined sculpture. And as the program moved forward, the mandate was clear. The best part is no part. Every wire, every bolt, and every auxiliary tube on the Raptor 1 was put on trial. If a component couldn't justify its existence with absolute necessity, it was destined for the deprecation list. The transition from the spaghetti of the Raptor 1 to the streamlined power of the next generation would not just be an upgrade. It would be a fundamental reimagining of what a rocket engine could be. And the era of the spaghetti prototype was coming to a close, and the era of simplifying the complexity was about to begin. End section break. Raptor number 2, simplifying the complexity.